This chapter is all about number theory and integers, and we're just kind of going to go into depth and looking into prime and composite numbers, integers, LCM, which is least common multiple, but we'll get there. Okay, so for the first problem, we have a chart and we see 2 through 11, and what we're doing in this is we're testing for divisibility, and each number has its own rule, and most of them are pretty well known. Like 2, for example, is known that if the number ends in an even number, no matter the length of the number, it is definitely divisible by 2. So our even numbers are 0, 2, 4, 6, 8, and 10, and then that pattern just continues on. So for this one, it ends in an even number, and this was already filled in. So yes, it is divisible by 2. Even number divisible by 2, and this is an odd number, so it is not divisible by 2. And this is the same pattern goes on throughout all the numbers. We can just look at the last number and see if they're divisible by 2. It's really quite simple. For 3, what we want to do is we're going to want to add up the sum of the numbers to know if it is divisible by 3. I have written that down here. Let's see. And it is right here. This is my chart that I filled out. And then right here we have, I've written down the first number, 6 plus 8 plus 4 is 18. And 18 is divisible by 3. It goes into, 3 goes into 18 6 times. So the answer would be yes, the sum is divisible by 3. And we can go through and we do the same thing for the next number. We've got 2 plus 0 plus 6 plus 4, which is 12. And 3 can go into 12 4 times, so 12 is divisible by 3. This pattern, again, this is just another pattern that is repeated multiple times over and over for each number, no matter the length of the number. This will work. And then I went ahead and did 3 and 9 together because 9 is kind of the same concept. You want to see if the numbers are divisible by 9. So we already got it written down because we just did it for 3's. So we got 6 plus 8 plus 4, which is 18, which yes, it is divisible by 9. And that, of course, is another thing that just repeats. The pattern is repeating throughout all the numbers, regardless of the length of the number. We can do the same kind of thing for 8's, but 8's are just the last 3 digits, and I know I'm going out of order, but this is just how I did it because I saw a pattern as we're starting to do the divisibility. 8's we can go ahead and look at, and we can just do the last 3 digits. So for this, we've got 6, 8, and 4, which is just 3 digits, and that's 18, which is not divisible by 8. And then we've got 6 and 4 and 0, but of course we're not going to need the 0. And 6 and 4 is 10, which is not divisible by 8. So of course that's just another repeating pattern. 4 is very, very similar to 8. But it also has a little trick as well. A number cannot be divisible by 4 if it is not an even number. So we've only got one odd number, so we can just go through and cancel that one out because we know it's not going to be divisible by 4. But for this one, we just do the last 2 digits, which would be 8 and 4, which is 12, which is divisible by 4. 6 and 4 is 10, so it is not divisible by 4. And again, this is just another repeating pattern. 5 and 10 are also very simple. 5, if it ends in a 5 or a 0, is divisible by 5. So we've only got one number here, and that's this one up here. 10, if it ends in 0, it's divisible by 10. So this one up here ends in 0, so it is divisible by 10, and is this one as well. I'm sorry, I missed that one. And then 7 is a little bit trickier than the rest of them. And 7 is, I did it right here. So what you want to do is you want to double the last number. So if the number is 684, which is right here, you double the last number 4, and it's 8. So then you go ahead and cross out the 4, and you subtract the 8 from the remaining 2 numbers, which is 60, and 60 is not divisible by 7. And then we do the same thing regardless of the length of the number. You can go ahead and do the same thing. As you see in my work, the process remains the same. It's a repeating process. It just gets a lot longer, and there's a lot more steps because these really big numbers, we don't know just by glancing at them if they're divisible by 7. If you do, that's fantastic, but I personally do not. And then 6s, I saved for last because you can divide a number by, or a number is divisible by 6 if it's divisible by both 2 and 3. So I would just look up at my chart here and see if it's yes and yes, then 6 would yes. If it's yes and yes, 6 is yes. But then if one has a no, because it's not a number, so it's not divisible by 2, so this one's a no for 6 as well. So this is all that we need to do for looking at divisibility. It's quite simple. It's fun. I like to do the 7s, and they all kind of have a repeating pattern, and once you figure out that pattern, it takes nothing to go ahead and find the divisibility of any number. Okay, problem number 2 is something that is called casting out the 9s. And all we're going to basically do is we're going to check our answers of arithmetic problems that we have set up here and make sure that they are correct, and I will show you how to do that. That is done on this page right here. So we've got 416 plus 7,490 plus 69,844 equals 112,790. So what we're going to want to first do is we're going to want to get to the sum of these numbers and divide them by 9, and then our remainder is what we are really going for. So for 416, we have 4 plus 6 plus 1, which is 11. So that's 1 9 with a remainder of 2. And then this next number is 7 plus 4 plus 9 plus 0, which is 20, which is 2 9s with a remainder of 2. And then we've got 6 plus 9 plus 8 plus 4 plus 4, which is 31, which is 3 9s with a remainder of 4. So then these are our remainders right here, the 2, the 2, and the 4. And since this is an addition problem, we add the remainders together to get 8. So now we're going to see our answer that we got to this addition problem. We're going to check it to see if it's correct, because we want this remainder of this to be the same as this, which is 8. So we're going to just add these numbers, which is 1 plus 1 plus 2 plus 7 plus 9 plus 0 is 20, which is 2 9s with a remainder of 2. And 2 does not match 8, so this number is incorrect. So all that I did was I went through and re-added these, as you can see right here, and I got the answer of 77,750. And when I redid the math, I got 2 9s with a remainder of 8 after adding all these together. And 8 is the same remainder, and that is how we know that is correct. It is the exact same process for number 2. Number 3 is almost the exact same. The only difference is after we go through and we add all the numbers together of each individual number, we subtract them because this is a subtraction problem. So we subtract 8 from 2 and get 6. And then, of course, this was an incorrect answer, so I just subtracted it and got the remainder of 6. 4, again, same concept, just a little different because we're multiplying these numbers together. And we would multiply together 4 and 8 to get 32. And what I did was I went ahead and broke down 32 again just to get the remainder of 5 because it's 0 9s with the remainder of 5. And that is it. That is how we cast out 9s to check our answers. Problem number 3 is looking at greatest common denominator, or GCD, using these colored rods. And I don't have any physical colored rods to show you, but we can kind of look at the picture here. So for this one, it says show which rods will measure the 9 rod. And that means what rods can we fit into this 9 evenly. So we can fit this one cube or rod into the 9 times. So that would be one of the GCDs. We can fit 3 in the 9 3 times. So that would again be another GCD. And then of course we can fit 9 onto 9 one time. So then our denominators would be 1, 3, and 9. And then for 6, we can fit 1 on there 6 times. We can fit 2 on there 3 times. We can fit 3 on there 2 times and 6 on there 1 time. So that would give us 1, 2, 3, and 6. And then if we were to put those numbers together, which I have done right here, we've got 1, 1, 3, 3, 2. But as you can see, like we're looking for the greatest common denominator, which in this one is 3 because it's the biggest thing that they have in common. They do have 1 in common as well, but 1 is not the greatest because 3 is bigger than 1. And then for this one, like for the letter D, this is creating a train, and that'd be if we put 10 and 8 together. So we just pretend that it's 18, and then we can go ahead and find the multiples, the factors that go into 18, which would be 1, 2, 3, 6, 9, and 18. And then, of course, this shares a denominator, a greatest common denominator, with 9 and 6, number 1 and number 2. So this can be used to find greatest common denominator really easily because we just can visually see what can fit into what. Like we can see that 2 will not fit into 9 visually because we can try to line up 2 cubes with a 9 and we'll have 1 extra 2 or 1 less 2 than we should have. Okay, number 4 is finding the least common multiple by factorization. And to do this, I did not quite understand this method right here. I just used the method that I learned while I was in school, and that's this tree factorization, which I have done right here. And so I did 48, 25, and 65. So for 48, I did 2 and 24, and then 2 and 12, and 3 and 4, because 24 is not a prime number, so we'd have to break it down more. 12 is not a prime number, so we'd have to break it down more. 4 is not a prime number, so we'd have to break it down more. And so that gives us 2, 2, 2, 2, and 3, and I've written that down right here. 25 would be 5 and 5. 65 would be 5 and 13. So then I went through and I have written down all of the numbers that we got right here, just aligned. And then we're going to cancel this 5 out right here because we've got 2 right here, and we don't need that one. So that would equal 2 to the third power times 3 to the first times 5 to the second times 13 to the first power, and that would be our prime factorization for the least common multiple between these numbers. And then for B, it's the same exact concept. We'd cancel out these 2's because we've got all the 2's right here. What I went ahead and did, I did this all in the calculator, except for right here I have written down the number, which is 14,520, is what this equals. And then what I did to check this was I went into the calculator and divided each of these numbers by this number to make sure that it divides into it evenly, so that I know that I'm not wrong in the fact that they do evenly divide into 14,520. Problem number 5 is asking us about gears and the rotations of the gears, and for this we kind of combined LCM and GCD. So what we do is I have all my math written down, but let's read the problem first. Is in a machine, a gear with 48 teeth is engaged in a gear with 48 teeth, with teeth A and B on the smaller and large gears respectively in contact as shown. How many more revolutions will the small gear have to make before A and B are in the same position? So basically, we're looking for the greatest or the least common multiple to see how many times it's going to take 48 to spin to get 84 again to me. So here's how we can do that easily. Here I went ahead and did the factor tree of 48 and 84, and we've got 2 and 24, 2 and 12, 3 and 4, 2 and 2, 84, and then went ahead and have written down the numbers, the prime numbers that are in each of these numbers, and we cancel out these 2's and that 3. We're going to cancel out this 3, it doesn't really matter, but we get 2 to the 4th power times 3 to the 1st times 7 to the 1st, which is 336. Then I went through and divided each of these numbers by 336 to make sure that they divide evenly into these numbers. And then we're going to divide the smallest number by the least common multiple to find the greatest common denominator, which is 7 in both of these. Excuse me, it's not the least common multiple, it's how many times it takes 48 to get to 336. So basically 48 times 7 is 336. And that would be the answer that we need to have A and B meet each other again. The last problem is this magic square, and what you want to do is you want to have a magic number to make this square have the same answer throughout diagonal, across, and vertical. And so what we do is, what I've noticed by looking at this is these are all negative numbers with an exception of 0 and 1. So we know for a fact that this is going to be a negative number as our magic number. So what I went ahead and did was I put a -7. Like, that was the one that I wanted to get rid of first and try to place first, because that was my quote-unquote biggest number, although it is technically the smallest, we're just going to say it's the biggest. Because we're going to put it by the 0 and the 1, because the 1's going to make it have less. So we need to go ahead and find a way to work around that. I just did guess and check to get this, and it did take a while, but I eventually found -9 is the magic number, and everything works across. We've got -4 and -5, which basically just add those. You get -9. -7 and -3 is -10, but then you got the 1, and that makes it -9. And then same thing, -4 and -6 is -10, and then you got the 1, and then we've got -9. And it is that simple, and that is all we do to find the numbers for the magic number for magic squares.